All right, let's go ahead and get our session kicked off today. So I want to thank you all so much for making the time here this morning to attend our session on Rust on bare metal. As you may or may not know, we've been doing a lot of Rust training sessions since the springtime. We've thrown in a couple of other topics too, some database stuff and web programming, but it's all mostly been Rust programming. And we've really just been looking at using Rust just to write regular programming code that simply just runs on a computer. But a big part of Rust development, or a big reason why we use Rust, is kind of as a replacement for languages like C++ and C. And a big area where C++ and C are used is in embedded programming microcontrollers. And so the natural question is, can we do this in Rust? Can we get those memory safety benefits of Rust and be able to program these embedded devices? And the answer, of course, is yes, we can. And so I thought it would be fun here to do a session on that. We'll see what the level of interest is. I've got some plans for some future sessions on this if people are interested. But I thought it'd be fun to kind of try this out for our session here at the beginning of October. Now, this is going to be a little bit more challenging in a logistics sense than a typical presentation. If you've attended the past ones, I typically just share my screen, we look at the code and run things. But for this microbit and embedded Rust presentation, I wanted to be able to show you the actual microbit that we're going to be using here. And so as we go through the presentation, I'm going to have to stop sharing and resharing my screen so that I can make the video part for the microbit larger and smaller, depending upon where our focus is. Of course, the challenge with that is I'm going to have to constantly adjust settings and stuff as we're going along, and it would be very easy for me to forget to turn on one thing and turn off the other in the course of the presentation. So the reason why I'm mentioning all this is I'll do my best to keep everything running smoothly, but I'm sure at some point I'm going to make a mistake and talk about code while I'm not sharing the screen, or talk about the microbit while I'm still sharing the code. And so if I make any mistakes like that along the way, I just ask for your forgiveness ahead of time, but we'll do our best to manage the logistics of this. This is my first time ever doing a presentation that involves like a separate camera and a device. Like I said, most presentations are just sharing the screen and talking about code. So as we're going through this process, I've done a little bit of practicing and stuff ahead of time, but just bear with me if I make any mistakes in terms of remembering to share versus not share, so on and so forth. With that said, let's go ahead and dive into our content here. So a couple of things about these presentations before we actually get into the programming stuff. So Training for Programmers delivers team-based software development training to companies around the world. And that's great. We love doing that. And I love teaching corporate classes. It's how I pay the bills. But not everybody can work for a large company. Not everybody works for a company that offers training. And so back in the springtime, I thought it'd be cool if we could offer some of the same type of training that we'd offer in a corporate environment, but just kind of offer it for free here through a webinar type format, and then posting the videos up on YouTube. And so the name for this series is this Programmer to Programmer series. So I'm a programmer just like you, and I'm sharing with you the things that I've learned and trying to incorporate some of the aspects that you might find in a professional corporate training type of environment. The goal for the training sessions is that anybody can take them, right? So you just need a web browser and internet connection. Generally speaking, for most trainings, you can even code along with me through like GitHub code spaces. But because this requires actual hardware that you have to pay for, this is just going to be a demonstration. But most of the time, you're able to code along with me. The idea behind this is that instead of everybody having to like move all over the world to get some big corporate job to then get great training, you can get this training from anywhere. So from the comfort of your home, the community that you're in, we want to empower people where they are to bring happiness and prosperity and things like that to where they already live. Throughout these trainings, we occasionally incorporate some AI tools and stuff to kind of talk about how AI can help us. I don't really have any big plans for that for this particular session, but we do talk about those things from time to time. We would love for you to connect with us. We have our website, trainingforprogrammers.com. We're on LinkedIn. We have our YouTube channel, and of course, our email address. And what I'd like to do here real quick in the chat, just bear with me for one moment. I'm going to put a direct link to the YouTube channel in the chat. And the reason why you want that is I'll be posting the recording for this to YouTube after today's session. And then if you'd like to visit us at our website, you can do that there. Okay. All right. Wrong direction. Okay. So the type of content that we're covering today would be content that you might find in a Rust Essentials or a Mastering Rust type of class. The embedded content is something that we cover as like an optional add-on. So for example, I've got a class coming up in a few weeks on Mastering Rust. And in that class, they wanted to do some embedded programming. So we'll be using the microbit like we're going to be using here to do that programming. So if you do work for a company that has a team of programmers and you're looking for professional, paid type training, definitely reach out to us. We would love to work with you and put together a class that's customized to your needs. Before we get into the actual content, couple of things. Number one, thank you for registering and attending. We always appreciate it when people register for the event, but also then attend the live session as well. Once this session is over, review the demos. We have everything laid out nice and neatly on a nice GitHub repo with documentation and stuff, as you'll see. When the session is over, you have access to all the source code, all the documents. You can go off and practice this on your own and continue to deepen your skills. Within 72 hours of the event, I will have the video published up on YouTube. And for those who have attended the live session, you will receive your badges. I don't really send out an email anymore saying that it's posted. You can just go out to YouTube and you'll see the recording out there. And those of you who are here for the live session will get a badge for attending, so you'll get an email for that. If you'd like to stay up to date on things, follow us on LinkedIn. Also, if you go to trainingforprogrammers.com, you'll see a place where you can sign up for our daily email. And as part of that list, you'll be notified of upcoming sessions. I will have a little end of class survey I'm going to ask you to fill out. It's completely optional, but it's a great way for you to offer feedback on whether or not you'd like more videos on topics like this or other topics you might be interested in. It just allows us to get a sense of what the community is looking for, so we can be thinking about the content that we produce for the community in terms of these free sessions that we do. All right. So let's do a quick little overview of Rust and embedded Rust, and then we'll get into the actual coding. So for those who are not familiar with it, Rust is a systems level programming language focused on speed, memory, safety, and parallelism. The thing that makes it different is its unique ownership model to enable memory safe programming. It supports zero cost abstractions. It allows basically very high level features without the performance penalties you might incur in other programming languages. And really, it's used for a wide range of applications. We really focus in on this idea of systems programming, and that's really what we're doing today in terms of microcontroller programming. But you can use Rust to build web applications. You can use it really for anything. It's definitely a great language for a lot of different purposes, and in this case, embedded programming. So a couple of things here, Rust on bare metal. So Rust on bare metal is just a cool way of saying we're doing embedded programming on a microcontroller with Rust. Essentially, there's no operating system. So we're just running our Rust program directly on the microcontroller. That presents some unique challenges that we'll talk about as we go through. But the goal is we want to be able to utilize Rust for the benefits that it provides, like memory safety and performance, concurrency without data races, bare metal development, and cross-platform tooling. So I'm doing everything here today on an M1 MacBook Pro, but you could do all of this stuff on a Linux machine or a Windows machine as well. It definitely works in a cross-platform kind of way. And of course, in terms of running the code, we'll be using an ARM Cortex M processor, but you can use other types of embedded architectures as well. Okay, let's go ahead and get to the actual coding, right? So let me bring up my web browser here. Actually, let me escape out of that first. There we go. Okay, so I've got a code repository that I'm going to drop here into the chat for everybody. If you want to go ahead and load that up, I believe I have marked it as public, so it should be there for you. So this repository, before we even get into all the content and stuff, let me just kind of walk you through what's in this repository. So one of the things I try to do for these sessions is not just, do a quick little demo of something and then leave you with nothing to walk away with, right? The goal of this, while it is to, there's a little bit of a marketing part to it, telling you that I offer team training classes. The real reason we're doing this is because we want you to walk away with content that you can actually go and work with and learn, just like you'd have in a corporate training or professional training type of class. So this repository is set up along those lines. In the courseware part, I've got a link to the microbit board that you can buy on Amazon, and the microbit plus the breakout board includes a bunch of other stuff too that you can also get on Amazon. These are not affiliate links. These are just regular old links. I'm not getting any money if you buy it off of Amazon. Just a convenience to go to Amazon and buy it. Now, depending upon the country you might be located in, I'm not sure if it's the same product links or anything like that. So you might have to look for other means to get the microbit. But if you'd like to purchase it, it is available there on Amazon, and I've provided you the direct links to the specific ones that I have personally purchased. Both the individual board, but also the board plus the breakout board and a bunch of accessories. Now, the content that I'm going to go over here is not content that I've completely created from scratch myself. Just like every other programmer out there, I use existing code libraries, existing documentation, both for learning purposes, but also for real projects that I work on. And so what I've done here is I've included right at the top, before we even get into our specific content, I've got the links to like Rust, the microbit itself. It's actually like a real organization. You can go check out their website. The embedded Rust book, the discovery book, and a library called Probe RS. Most of the content that we're going to be looking at here in today's session really originated from the discovery book here. And if you go to the discovery link, you'll see it has a link here to the read the newer book using a microbit, which is what we're using. And it actually literally goes through the whole process of setting everything up, giving you examples. Now, what I've done is I've taken some of this content, added to it in a sense in our code repo, and you'll see what I mean when we go over there. But if you're looking for like just this comprehensive book that the whole community is aware of, this would be the discovery book. The discovery book is the book that you would want to look at if you're really brand new to embedded programming in general. There is actually a more advanced embedded Rust book. We won't be referencing that in this class, but you can check that book out, and that definitely goes deeper into some topics. But if you're looking to like get started, you've never done embedded programming, you want a really simple way to get started, this is the book that you would want to take a look at. So I've got a link to that here directly inside of our content. Now, what we're going to be doing is we're going to be looking at the documentation that I've specifically prepared, as well as my version of those demos and some other things. And we'll go through and talk about these and kind of see how all of these work. Now, if you're getting started with literally nothing, like you haven't set up Rust, you haven't installed the tools for doing bare metal development, I've got a link here to 2 markdown documents that I've created. and they actually go through the process of setting up Rust on Linux, Mac OS, Windows, and Windows WSL2. And you can go through here, and it's got the specific instructions for setting up Rust as well as Visual Studio to make sure that you can have a full-blown Rust environment. These are the instructions that I use for my actual Rust courses that I teach for companies. The second document is installing the bare metal project tools. So there's a number of tools that you have to install in order to do the bare metal programming. First of all, you need the LLVM tools. It allows you to convert your compiled Rust code into a binary that can then be loaded onto your embedded device, in our case, the microbit. So this is actually a Rust up component, and it adds in those LLVM tools. Then once you have those tools installed, then you have to install the cargo bin utils, and basically this is like a Rust crate that wraps up all of that LLVM functionality. And then we have to install another tool called probe RS tools, and this is to have the ability to flash firmware and stuff to the embedded target, supporting running, stopping, debugging, things like that on your microcontroller. So probe RS is really what kind of connects it all together. Once you've got those 3 tools installed, you can use the cargo embed command to do the various things like build your project or push it out to the device, so on and so forth. Now, because we are working with hardware connected to our system, there are some operating system specific things that you might have to configure. So I've included these instructions here for Linux, Mac, and Windows. It kind of lists all the things that you need to go through and configure depending upon the operating system that you're working on. I have actually gone through the process of setting this up on Windows, Mac, and Linux before, not just my Mac that I'm on at the moment. So everything should work. If you go through and run the instructions and you run into any problems, don't hesitate to put an issue up on the repo or reach out to me at the community email address. I'll be more than happy to make any fixes or adjustments if I've made any errors in the instructions. So you can check that out. I'm not going to walk through that here for our time together, but when you're setting this up on your system, you can do that. Now, one of the things that the discovery documentation doesn't really have is it doesn't really have like a step-by-step on how to create a bare metal project in Rust. It has you clone an existing repository, but it doesn't walk you through the process of what you would actually just need to do if you wanted to start with just a blank project and make it work with the microbit through the embedded programming. When I was first learning how to do this, I actually stumbled a little bit trying to figure out what I needed and what I didn't need in order to make it work. Like I could copy the project from the discovery repo, but if I started with a blank project and looked at the discovery repo, the things that I needed or didn't need were not always readily apparent. So one of the things I would encourage you to do if you want to start working on your own bare metal projects is take the time to really walk through this one here. This is something that'll actually add a little bit of value beyond what the discovery offers for you to set up that project. So some of it is simply just standard Rust stuff to create a project. But then down here, I've got the listing of the dependencies that you'll want. By the way, one thing you'll notice in the discovery is it gives instructions for microbit version 2 and version 1. I only provide support for version 2. It makes everything a little bit simpler. You get rid of all the feature flags and things like that. So everything we'll be talking about here is with microbit version 2. One thing I want to highlight for you, in embedded programming, I have found that version numbers matter a lot more for crates than it does in other kinds of programming. You know, when you go to work on a project and you install a crate, you can just install it and get the latest version, and usually it works fine. With embedded stuff, things aren't always as flexible. So when you see people offering examples for embedded projects and you want to run them and stuff, or you want to use some of those features in your own project, pay close attention to the version numbers of things, that can be significant. Now, in this case, I've got specific versions we're going to be using, but just so you know, I am using the nightly build of Rust. Sometimes you'll see in these examples where they'll tell you to use some really old version of Rust from like 5 years ago to run these embedded projects. I've done all of my work here using the nightly build. So you should be able to use the most recent build of Rust itself to run most of these things. I'm not going to walk through what each of these individual packages does, but I have provided a description here for each of them so you can go through and read those. Now, one thing that is important to be aware of in a bare metal project is you'll need an additional TOML file called embed.toml, where you'll have to do things like define the chip that you're using. So you actually have to know something about the microprocessor, or the microcontroller, and the board and stuff that you're using to configure these things. If you're using the microbit, of course, all of that information is like published in every example you'll find. But if you're using something other than a microbit, take the time to understand which processor it's using, whatever the various chip identifiers are. You'll need that information to just simply do a build and push things out. Okay, we'll come back and talk about the RTT here in a moment. Another thing that you need specifically, at least for the microbit, is you have to have the memory layout of the target device. I think most devices require this memory layout, but I've seen in some cases where there are some devices where you don't explicitly have to list it. But generally speaking, you've got to have a memory layout of the device. And so this is just a little text file, memory.x, that you add to your project. And this is the correct memory layout here for the microbit. The only reason I know this is the correct memory layout is because this is the memory layout that's given as part of the examples. This is not something that I came up with on my own. So whatever device you're using, you'd have to look up that information. Okay. Now, the next thing you're going to find is there's a build RS file in our project. And the only thing this really does is it copies the memory X file. It configures a couple of other things as well, but it's really just used to copying that memory X file to our output directory. So in a Rust project, if you ever see like a build RS file inside the root folder of your project, that's just a code used as part of the build process. And in this case, copying that memory X file. One last thing you'll need. See, I told you it's a lot of little things here to get this up and running. Is you'll need to create a folder called .cargo. And inside of there, you'll need to create another TOML file called config.toml. And here you're going to specify your build target, and we're going to specify the various flags for the linker, as well as other information like the chip and stuff. Now, this part here can be a little bit hard or a little bit confusing to get working. I did not come up with this configuration on my own. I copied and pasted this configuration from other projects. However, different projects will have different configurations, oddly enough. So this is typically the one that I just go with and use. I'd like to tell you I have some great explanation over all the little pieces and parts here, but this is just something that you have to have in order for the linker and everything to work correctly. Now, let's take a quick look at this code. And then what we're going to do is we're going to go over to our actual VS Code, and we're going to start taking a look at the code over there. So this is kind of like a hello world microbit application. And there's a few things here I want to highlight to you. So first of all, you'll see at the top, I have a macro here for deny unsafe code. In this example, we're not going to allow any unsafe code. But in more complex examples, having unsafe code is something you will commonly see in an embedded program. So even though I have this marked with unsafe code here for the little hello world, just know later on, we're going to be removing that macro and we'll have unsafe code, especially when you get into things like with interrupts and working with trying to create your own heap allocator and stuff. All of those things require unsafe Rust. All unsafe means is we're just not enforcing the borrow checker for that code. So instead of doing memory safe programming where the borrow checker is being enforced, for unsafe code, the borrow checker is just not being enforced. And by the way, those unsafe code blocks should be kept to a minimum, otherwise you lose the benefit of working with Rust. You'll see we're bringing in this Cortex MRT entry right here. So your embedded program doesn't have like a usual main function like you'd have in a Rust program. Instead, we use this entry macro here to identify that this function is the starting point for the application when it runs on the microcontroller. Now, this is one of the things when I was first working with this that kind of threw me off. I don't know about you, but when I look at most code and I see something being imported, but we're not using anything from it, I remove the import. Well, back when I first started working with the embedded stuff with Rust, specifically with microbit here, I saw this line of code in some of the simple demos, and I just thought, oh, the person who put that there must have made a mistake. They just didn't go back and clean up their code. No, you have to have this here. In order for it to have the information about the hardware, to do the build and everything else, you have to pull this into the project. Even though in this case, we're not pulling in things like the board and other things like that, we still have to have that use statement. So if you were to take this code, copy it to your machine, and basically say, okay, I'm going to take out this line and take out this line because we're not using them, that would be a huge mistake. You have to leave that in there because it needs that information in order to do the build. The RTT logging is basically a convenient way to have the microbit send log data to us in our console when we run our program. So in this case, the log data we're going to be sending is just the message, hello from microbit. This RTT init just initializes that RTT logging system. We'll talk in more detail about that here in a moment. And then finally, you'll see this last piece here. One of the things you have to consider when doing embedded programming is how you want to handle panics. And so there's a number of libraries like Panic RTT Target, which will provide functions that define how you want to handle the panic behavior if a panic happens in your program. You'll see where these things are automatically pulled in, and all they're doing is registering a panic handler or other things with the overall application. So we're not using anything from it, but you have to have it there. My biggest mistake getting started was omitting this line, and stuff just did not work for me, and it was very frustrating. Okay, so now that we've talked a little bit about some of the gotchas of getting up and running, let's actually take a look at some of these projects and actually run them here on the microbit. So I'm going to come over to VS Code, and I have my code opened up here. Okay, so this is all the code that's in the repository just on my local machine. Let me close that real quick, and we'll come into Hello Microbit, and let's take a quick look. We already looked at all of this code, although I did add some comments here for the real-time transfer. So that RTT stands for real-time transfer. It's really just a logging mechanism, and that's how we're going to be using it for our demonstration here. Now, one thing I will mention is that at the end of your embedded programs, you will always see an infinite loop. So with an embedded program, it never really exits. It just goes into an infinite loop. Now, that infinite loop might be doing something useful, or if the program just does a couple of things and that's it, then the infinite loop just runs until you reset the program and have it run again, or replace it with a different program. So when you see that infinite loop at the end and there's no return statement, that's not a mistake. That's just part of programming in the embedded environment. Let me talk about the no standard here. This is probably going to be one of the most difficult things for you to adjust to when you get into the embedded programming. You do not use Rust's standard library when doing embedded programming. That standard library provides a lot of stuff, like the vector, the ability to do heap allocation with box and stuff like that. That's all provided by the standard library. But the standard library requires an operating system in order to be used. When you do embedded programming, microcontroller programming, there is no operating system. The only code running on the microcontroller is your code, which means all the usual facilities and services and memory type services that are provided by an operating system are not provided in a microcontroller or embedded environment. So we have to turn off the standard library and not reference it in any of our code. For very basic applications, this won't be a big deal. But if your code is making use of things like vectors in box and stuff like that, that's when you'll start to realize, oh, wait a second, I don't have the standard library anymore. So we'll talk about some alternatives of things that we have to use in order to work around that standard library not being present. Okay, so now that we've got this application, I want to run it on the microbit. In order to do that, I first have to hook the microbit to the computer, and then I can basically build and flash the microbit with the output from the build. So here's what we're going to do. I'm going to stop sharing here for a moment. I'm going to come over to the microbit, and you should be able to see me here. I've got the microbit right here. Now the camera that I'm using is a manual focus camera because I don't want it auto focusing on me. So I'm going to, if I ever pull it up too high, you'll see it'll get a little fuzzy, but I'll try to keep it down here so you can see everything clearly on this. This is the microbit itself. You'll see right here there's a USB micro USB connector that we can plug our micro USB cord into. It provides it electricity and the ability to flash it and receive the log data back over that connection. On the bottom side, you'll see there's two buttons that we can click, and we'll take a look at demos where we can click them. There's also a 5x5 LED array that will be lighting up through the use of our programs. Now, there's a lot of other stuff on here that you can make use of. Because of our limited time together, we're not going to be looking at the accelerometer or the compass. Also, you'll notice here, obviously, you can connect other external things to this. There's even a nice breakout board that you can get that allows you to then, use a bunch of pins and connect to breadboards and things like that if you want to. But we're going to focus mostly just in on the buttons and the LEDs and on the other aspects of doing embedded programming. What I'm going to do here is I'm going to take my micro USB cord here. I'm going to plug that in like this. And then once that's plugged in, I'm going to come over to my computer here. And I've got that plugged into the USB port on my computer. And you can see it's running a program that's already on there. And you can see the lights that are lighting up there for it. Okay, so there's our little microbit doing its thing. All right, so let me come back over to here, and I'm going to share my screen again. Okay, cool. So how would I go about actually running this program on the microbit? So I'm going to come down to here and open up a terminal window. I'm going to change into our project folder for this first project. And I should be able to say cargo embed. Sometimes you'll see where cargo embed is followed by additional arguments, such as the target device, stuff like that. The reason why I don't have to include those additional arguments here is because in this config toml file, I specified the target as part of the config file here. I don't have to specify that on the command line. If you go and look at other demos and they have a longer cargo embed and you're wondering why this one's shorter, it's because of the it's because of the config toml and setting the target inside of there. So if I run this, it's going to build it, and you'll see down here where it did the erasing and then flashing it. And this is our kind of our endless loop of saying hello from microbit. So this is that RTT transfer. This code is running on the microbit, sending me the log and printing the log here in the terminal. You'll notice over here, let me stop the sharing here for a second. You'll notice over here now, if you look at the microbit, those lights are no longer flashing. So the program that was previously flashed to the microbit has been removed and replaced with the new program. So you don't really install like multiple programs on the microcontroller. It's really just one program that goes on there. So if you have another program and you replace it, the other program goes completely away. Remember, this is not like a This is not like a computer where you've got an operating system and multiple processes and things like that. This is really your program and just the chip, and then whatever memory it provides. And the chip doesn't even provide like real memory management like you might have in an OS. You have to do all of that really yourself if you want to have like a heap allocator and stuff like that. Anyways, you can see that program has been flashed and has gone away. Now, back over in our terminal, let me share my screen again. I'm going to go ahead and hit Control-C, and that will stop the execution. See here right at the end before it displayed the terminal, you can see where it said erasing and then programming. So that erasing was removing the original program. The programming was flashing the new program onto the microbit. Okay, so now that we've seen kind of a hello world type of program, let's go and take a look at lighting up one of the LEDs. So I'm going to change folders here and go to LED microbit, and then we'll say cargo embed, and we'll let it erase and program it. You'll see I have my hello from microbit again there. And then what I'm going to do is stop sharing here for a moment and show you the actual functionality here. So you'll see it's now doing the going around the square, maybe. I'll bring it up a little closer. You can see the lights going there. It's a little fuzzy, but it's easier to see the light. So you can see that's going around like that. So that's the program that we have running, and that's the program we're going to take a look at here in the code. So let me share my screen again. Okay. So in our code, you will notice that we are getting access to the board. So remember before where the microbit was simply microbit as underscore? Well, this time we're pulling in other features from the microbit. So we're pulling in the board, the display, and a timer. So the first thing you see here is we're getting access to the board. This board struct that we're going to get is going to give us access to all the different features and capabilities provided by the microbit. Now you'll notice here we're saying take.unwrap. This is actually going to be take itself actually returns back an option. So if it can't get access to the board, it will return back none. You can only call board take one time in your program, and then once you get access to the board, that's the only time you can call that function. So you don't call board take multiple times. Down here, we're going to create ourselves a timer, and then we're going to create ourselves a display. Okay, you'll see how the display here is taking the display pins, and the timer is getting access to the timer on the board. Remember the LEDs here. It's a 5x5 array. So we're going to initialize all of the LEDs to be 0, so they're turned off. And then we'll use this previous LED so that we can turn on the next one, but turn off the previous one. Let's come on down here and take a little bit of a look here at the code. So first of all, we've got some stuff here that's really just standard Rust. So I've got my pixels.iter, which is basically going to give me a bunch of reference tuples here. If you scroll up, you'll see pixels.iter is basically just an array of tuples that represent the LEDs on the outside of the box. That's why you'll see only the outside is being lit up. And so what we're doing is taking this array and we're iterating over it down here. One thing I've noticed in my embedded programming, because vector is part of the standard library and you can't use that in an embedded program, we have other ways of having vectors, but you can't use the one from the standard library. You'll find yourself using arrays a lot more. So if in your Rust programming, if you always default to a vector, even for something of a fixed size, you'll find yourself making use of arrays a lot more in your embedded code because you don't have access to that vector anymore. Now in here, what we're going to do is we're simply going to take the elements of the tuple to update the the array of arrays here for our LEDs, our two-dimensional array, and we're simply going to be updating these in terms of turning them on or turning them off. So this turns off the previous LED, this turns on the current LED. Then down here, we're going to call display show, and it's going to take whatever that new LED's value is, and then display that with the LEDs, and then we just save a reference there to the current lead. We save that out to the, not a reference, we make a copy actually. We make a copy of the current LED into the previous, so that when it iterates again, it can turn off that previous and then turn on the new current. So when you're looking at this code here, there's really nothing super exciting about it. The biggest thing really to mention is this grabbing of the board, understanding that now we're just trying to learn the API specific details of how to work with this board. One of the things with embedded programming, really with any kind of programming, is there are parts of it which are, how does the language work? What are the best practices for various kinds of operations, what have you? But then there's also just the plain simple technical part of what is the API provided to interact with this specific thing. And so you'll find a lot of times with embedded programming, you spend a lot of time looking up and understanding what these very specific APIs are to access the different features of the board or different features that you might have plugged into the board itself. How do you actually call those and work with them? Now, there's one part of this code that I really don't like, and if you've been in my other classes, you know that I make kind of a big deal about this. I'm not a fan of unwrap. Anytime I see unwrap in code, I want to get rid of it. So what I thought we would do for the next little demonstration here is, how would I go about getting rid of this unwrap? And let's take a quick look at that. So remember, we're using Rust, and so we want to leverage the features of Rust as much as possible to write the best possible embedded program that we can, right? We're choosing this language because we want the features of it. The problem with unwrap is unwrap just causes a panic if I'm not able to get what I'm trying to get. Now, ultimately, in my solution here, I'm still going to cause a panic, but I'm going to do this in a little bit more of a controlled way. Instead of just calling unwrap and then it blows up on me, I'm going to employ some Rust syntax to put a little bit more thought into how I want to handle this particular situation. Like I said, for me, unwraps are a red flag. Unwraps means when I see an unwrap in code, it means we haven't thought about how we're going to handle either error situations or situations where we get back a none. So let's learn a little bit of Rust syntax here and take a look at a way that we could handle this. This is not the only way, it's a way. So I'm going to use an if-let expression. You might have used like an if-let statement before, but you can actually use if-let as an expression. One cool thing about Rust is a lot of the traditional control flow type statements that you would just think of as just kind of organizing logical blocks of code, they themselves can be turned into expressions. So here what I'm going to do is I'm going to come into here and say if-let some board. So if we're actually able to take the board and we don't get back none, it's going to assign the board to this variable which is being declared here. And then you'll notice there's no semicolon here. This variable is going to be the return value of the if-let expression, and we'll assign it to this variable here so I can use it later on in my code. So in this case here, if I actually can get the board, assign it to this variable, and return that back and assign it to here, and then I can use it down here in my code. Now let's say I'm not able to get the board for whatever reason. Then I can handle this any number of different ways. I could print a log message like you saw before. I could panic. I could do some other form of logging or some other type of custom error message with additional data that I might want to include. But by doing something like this, I know that the programmer has thought about what they're going to handle with the none condition. Now, in this case here, am I really doing anything too much different than unwrap? No, but I'm showing that I'm thinking about it and actually actually handling it. That's just my personal preference. You're welcome to disagree with that if you'd like. The rest of the code is as you see it here. As you saw in the earlier example, I won't go into any more detail on that. Okay, let's talk a little bit here about how we would go about debugging one of these programs here. So what I'm going to do is I have in our instructions here, I have the process that you would go through to actually go through and debug. You have to do a little bit of extra work to do the debugging. You can debug with GDB, or you can actually debug directly inside of VS Code. So with VS Code, to do the debugging, you have to install this extension here. So in VS Code, if I go in and put that in, you'll see there's this debugger for ProbeRS. That's the software that does the flashing and debugging. We can add in a launch JSON configuration to do the debugging. So if I come over to here, let me, interesting, I don't have a VS Code folder. All right, well, let's do that. Let's create a new folder, VS Code, and let's do add configuration, ProbeRS debugger, and I'm going to copy the configuration that I have here. Copy that over into here. Okay, so now with this configuration here, I should be able to debug my program. And let's go ahead and come back over to here. And let's set a breakpoint here. I'm going to set a breakpoint right there. And let's see if it will let me debug this. So you'll see it's doing all the flashing and stuff automatically for me. And now I can debug. So I think this is probably, if you're more of a visual person and you like using VS Code as opposed to doing things from the command line all the time, this is probably a more convenient way to do your debugging. Or you could use GDB. And I'll have to go back and figure out why my configuration is not working for that. But anyways, you can also do the debugging this way. So the instructions for all of this, if you want to set it up on your own local system or for your own project, all of those are configured under here, under one of the markdown files that I provided. All right, so now that we've done our battling with our tooling, let's come on back over to here and let's jump into the the other examples that I have for you here on different features on the board. So we've got about 30 minutes left to go. I'm going to walk through these different examples. If we go over time a little bit, I don't have a meeting following this session, so I'll just cover these all the way until the end. If we need a little longer, that's fine. And then, of course, if you have to drop off or anything, the recording will be available up on YouTube. Before anybody drops off, though, I would ask you to do this. I know people don't like filling these things out, but it is helpful to me. And I'll go ahead and put that in there. It's a little survey. If you could just fill that out before you take off, that'd be awesome. And then I'm going to keep on going here in a second. But we do have a question, actually. You need to install some specific drivers for the board. Not really. In terms of like just the board itself and plugging it in and all of that worked fine. The only thing that I had to like install were just the development tools that I mentioned in the markdown documents. But there was nothing else that I didn't have to go download some microbit drivers or something like that in order for this to work. But I did have to download all that development tooling that I talked about earlier. Okay, great question. Thank you for asking. Okay, so what we're going to do now is let's go ahead and walk through these remaining demos that I have. My focus here is embedded, but I also want to talk about how Rust helps us do embedded programming. Just because this is just a way of making use of Rust, and let's see how Rust can help us out. So we're going to take a look here at the button press microbit little demo that I have for you. All right, and if we come into here, you'll see I've got a bunch of comments here in the code that you can come in and read later on to understand what the code here is actually doing. But we'll walk through it and do kind of a high level overview of what's actually happening here. So one of the biggest reasons, or one of the coolest things, I rather should say this, one of the coolest things about doing embedded programming is when you can hook up a bunch of peripherals to it, things like buttons and LEDs and accelerometers and compasses and GPS and temperature sensors and motors and displays and stuff like that. The microbit comes with some of these things built into it, so you don't have to go out and get a breadboard and buy a bunch of independent devices and wire them all up together. But you can do that, and they provide kits for the microbit that will allow you to do that. But we're just going to use the onboard capabilities here. In order for all of that stuff to work, though, you have to have a way for your controller to be able to talk to all those devices. And this is usually through some type of GPIO mechanism. If you were to go buy like a Raspberry Pi, like an actual one that runs Linux, or you were to buy like a Raspberry Pi Pico, which is just a microcontroller, or the microbit, what you're going to find is that all of these boards have one big thing in common. They all have this GPIO that allows you to connect in all these different devices. And there's a number of different protocols and stuff that are used to connect the devices up and allow you to access them. We're not going to focus so much on that in this particular session. But when you see this GPIO TE struct that we're creating here, this is the thing that allows us to talk to those devices. So you'll see here we get the board, and then on the board we get access to the GPIO, and then we're going to start configuring channels here for our interactions. So for example, here we have a button. So if I come back over to here, I'll stop sharing for a second. If you look here at the board, you'll see there's two buttons, okay? And we can basically connect these buttons to a particular channel, and then we can read data off of them when the buttons are clicked, right? So if you think about it, what does a button do when you click it? It basically allows current to go through the circuit. And so what you can do is you can basically write code that will respond to the current going from high to low or from low to high, right? So you can actually hook into that event and then have some code run in response to it. The act of hooking into that event is what we call an interrupt. So if you think about it, your program is running, somebody pushes a button and it interrupts the program. And then you can run code as part of that interrupt, like an event handler, and then do something useful or interesting for your application. So what you see us doing here is basically connecting in the channel 0. We're wiring up the button into channel 0. We're going to listen for the high to low, and then we're going to enable the interrupt to run when that button is pushed. So what's the code that's going to execute as part of the interrupt? And that's what you see right here. So essentially, we use this macro to mark this method as a method handling the interrupt. I'll come back to the free critical section here in a second. Let's just focus in on this code. Essentially, what we're going to end up doing is we're going to interrogate the board to figure out what event occurred. So in this case here, we're going to get access to our GPIO mechanism. We're going to get access to channel 0 and see if an event was triggered on channel 0. So what would trigger the event? It would be going from high to low on the button. So you click the button, when it goes from high to low, that's what would trigger the interrupt. In this case, we're going to run some code that prints some text out to the RTT, so we can see that we press button A, And then we're going to reset the channel so that we can have future events trigger it. Now, this is where we get into a memory situation. So there's only one GPIO. You can't, it's just like there's one board, there's one GPIO. If we had some type of embedded system that was running on multiple cores, or maybe we had an embedded system where we were doing some type of threading type of mechanism, we're not really doing any of that here. But let's say we had something like that. Or let's say you had multiple interrupts fire. We need a way of basically kind of blocking the execution of the program while we're working with this GPIO. We don't want other parts of the program, if it was some type of concurrent or other type of similar program, we wouldn't want to have different lines of execution competing over this shared resource. The way that we handle this in an embedded device is we create what's called a critical section. Whenever code runs in a critical section, we're basically blocking everything else. We're getting an exclusive lock. We're doing the processing that we're going to do. And then when we're done, we release that lock. And that's what's really happening here. So here, I'm going to get my GPIO. I'm going to check to see if the event was triggered. I'm going to reset it. And while I'm doing this, nothing else can get access to this critical section. Nothing else is going to be able to interfere with our interaction with the GPIO. Now, you'll notice here that we have .borrow, borrow, and asref. You'll notice we're doing runtime borrowing. So when we think about Rust in the borrow checker, there's the compile time, which is what most of us are used to and familiar with. And I'm not sharing my screen, am I? Let me share my screen again. So we have the runtime, we have the compile time borrow checker, which is what most of us are familiar with. But there's also a runtime borrow checker. Sometimes we don't know until runtime how some piece of memory is going to be used, especially for like dynamically allocated memory. And we have to control access at runtime instead of compile time. This is particularly true if we use types like the ref cell. So the ref cell allows what's called interior mutability. And when you use something like a ref cell with interior mutability, you have to check those borrow rules at runtime. So here you'll see where we get our mutex, or from our mutex we get our ref cell, okay? And then we're going to borrow it, and it's going to be a borrow reference. We're not moving ownership. We're just borrowing a reference to it, and we're getting and it's not a mutable reference either. It's an immutable reference, and we're getting our reference here to our GPIO, and then we're doing our work with it. So you can see here, making this GPIO available through this ref cell, through this mutex that's static. So static is basically like a global variable that's shared. So we have this shared resource that we can get this mutually exclusive lock on. And inside of it is this ref cell that allows us to then do the runtime borrow checking to get access to our GPIO, and then we can check the state of it, check for events, things like that, and reset it. And we don't have to worry about, if we had like a concurrent type application, we wouldn't have to worry about the other parts that might be running having some type of conflict with it. Now, let's come down to here and let's run this real quick. And we're going to say cargo embed. Okay, so I'm going to stop sharing. We'll bring the device up to here, here, and we should see, oh, that's right, we're not turning on the LED. I was thinking we were turning on the LED, but in this case, we're just printing out to the RTT. Let me share my screen again so you can see the RTT. Okay, so you see down here where it says button A pressed. I'm going to hit Control C. I'm going to run that again. Okay, now if I come over here and click this, there's nothing to see on the micro bit. It's just, you can see I'm pushing the button. And so that's an example of using a critical section to interact with, in this case, the button, and run some code in response to the button being clicked. Okay, let's take a look at another kind of interesting feature here. The ability to do serial communication. So the RTT mechanism, where we get these debug messages, that's really just a debugging mechanism for doing development. It's not the way in which you send data back and forth between the computer and the board. To do that, one way we can send that data is through the use of a serial connection. So down here, you'll see where we're going to go through and configure up our serial connection. I've got explanations for the different parameters you can take a look at following our session here. And then down here, we're going to send that data back and forth. Now, we have two ways we can do this. We can send the data byte by byte, or we can use the write macro and send like a whole string of data. But essentially what's going to happen here is once we set up our serial port and something is connected to that serial port, I can then use this macro to send a byte over the serial port. What this does is this blocks until the serial port is ready to write. So as you know, when you interact with hardware, it becomes a little more real world, right? In the real world, something might be preventing from that serial port from writing or whatever. And so your software tells it to write, but it can't in that moment. NB block simplifies the process of, okay, I want you to write this. And it waits until it's able to write it before continuing to execute. So instead of you having to write a bunch of code to do that, it'll do that for you. If any of you all have any like Python programming experience and you've ever used the method sendall with the socket library, you'll know that with sendall, basically you give it a string and it handles the details of sending all those bytes across until they're all finally sent. You don't have to write the code to see how many were sent and resend the remaining ones. That's kind of what NB block is doing here for us. We tell it to write this out to the serial port. It handles it and then returns control back to us once those bytes have been written, even if it has to wait a moment in order to be able to do that. So this is an example of writing. Down here we have flushing. As you know, just because you write something to the serial port doesn't mean that it's actually sent over the wire. A lot of times multiple writes are buffered and then kind of all sent at once. Flush basically tells it, go ahead and send the data out over the serial port. So how could we see something like this actually execute? So I'm going to come over to here and I'm going to say cargo embed, and we'll put the program out on the device. Then what I'm going to do is I'm going to come up to here and I'm going to take this command, copy it, come over to my terminal, and I'm going to bring up a list of my USB modems, which this is the actual device here, that this is the microbit. And then what I'm going to do is I'm going to use this minicom command. And minicom is one of the programs that we install as part of the setup. And I'm going to grab this device, run it, and now I'm in minicom. So now, if we come back over to here, let's see if we can get this to send. Okay, see how that popped up on the screen? If you can see my device here, I know the screen's a little small. You see this black button here right next to the micro USB? This black button is basically like the reset. It kind of reruns the program. So if I push that, each time I push it, you'll see it pops up the string in minicom. Now, I'll be honest with you, Minicom doesn't seem to work very well on my Mac for whatever reason. The only way I can exit it is to actually just exit the terminal window. But so it's kind of going off the edge there. You can't see anymore coming through. But the little button here, when you push it, will send that message back. Okay. Let me come back over here, and I'm going to go ahead and kill that window real quick. And we'll start a new window for our next Minicom session. So let's go ahead and take a quick look here at how this is working. So first of all, we get the board like we usually do. We set up the serial port, and then we're able to send those bytes across with MB block. Notice I am checking to see if I have an error, and if I do, then I panic and output whatever error message I think is appropriate. There's also a serial setup. Now, I did not create this file. I got this file from the Discovery project. This serial setup basically takes care of some of the details of setting up your UART port for doing the writing and the flushing and the reading, and provides a little bit of a wrapper to handle transmitting and receiving the data back and forth. Okay. Let's come over to the Echo server. This one's kind of neat. So the this server, the ECHO word is a wake word for one of my devices. So every time I use that word, the device speaks up. You might have heard that in the background. So we'll just call this our repeating server. It repeats back what you say. So our repeating server here is basically going to receive some data and then send that byte back to you. So we're going to send over a byte and get back a byte. You'll see here I'm using the serial read as opposed to serial write to be able to read the value. This will return back either an OK or an error. So the OK, I get the byte and then I'll process it. Error, I'm just going to panic and we're going to end the program. So I'll come back over to here and let's actually run this. And then let's do cargo embed. Okay, now we'll come back over to our terminal here. And let me do this. This is the problem with killing the terminal window. I don't get the Z shell history. Okay, and we'll copy that. Okay, now if this is working, I should be able to type into it a single character and get that single character sent back to me. Pretty cool, right? So I'm typing into it, it sends the character, and then I'm getting it back. And you can see received hello. All right, so a little example of a little repeating server there. Let's take a quick look here at reversing a string. Now, this one is important because it's going to introduce a limitation of an embedded program and then how we're going to overcome it. Remember, we mentioned before, there's no standard library in an embedded program, and you may not realize it, but there's a lot of stuff provided by the standard library, things like vectors and boxes and stuff like that. So let's say you do want an actual vector. You don't want just a simple array. How would you go about using a vector if you don't have it provided by the standard library? Well, you have to use an alternative implementation. We're going to pull in a crate here called heapless, and it basically provides us a vector data structure that doesn't require the heap. essentially what's going to happen is you're going to define kind of a fixed sized vector, but it's empty, right? So it has like, maybe a better way to describe it would be a capacity. So the vector will have a certain capacity, but then you interact with that vector normally up to that capacity. If you try to add something beyond the capacity, it will give you an error instead of just resizing the vector, because this is a heap list, so it's all memory allocation that's done one time. It's not dynamic memory allocation, so it's all static. So the heap list vector gives us the kind of the same type of API functionality. We just don't get that automatic resizing built into it. So if we scroll down, you'll see where I'm going to create a vector. It's going to have a size of 32. So we're good up to a 32 byte string. And essentially what we're going to do is we're going to read from the serial port into the vector until the vector is full, or we hit the enter key. If we hit the enter key, we're going to come down here, reverse the string, and output the bytes back to the caller. So let's take a look at how that works. So we'll go ahead and embed. I'm going to that, open up a new terminal window. It remembered at that time. Okay, good. So we'll go ahead and fire this up. Now I'm going to type into my minicom, and then I'll hit enter, and we'll get back the message. Just type in cool, hit enter, and you can see it comes back in reverse. So that basically read cool into the buffer and then came down to here, and when it iterated, it called reverse here, and we iterated over the vector in reverse and then wrote those bytes individually back out to the serial port. Okay. All right. So this gives us an example of being able to use a vector, but within the limitations of embedded programming and having to pull that vector from this other crate that that's called heapless. Okay, I'm going to skip over the snake microbit for a second because I actually want to talk about the alloc one first, and then we'll run the snake and you can see what the snake one looks like. So this alloc one is not in the discovery book. This is one that I threw in completely extra. I wanted you to see what it would look like to actually have a memory allocator and be able to use things like box. So if we don't have the standard library providing box to us, so just for those of you who may not be familiar, in the C programming language, you typically use malloc to allocate dynamic memory. In C++, you use the new operator. In Rust, you use box. All of those things are just kind of provided for you. If you've ever used a language called Zig, one of the things you'll quickly learn about Zig is Zig does not provide an allocator that's automatically set up and ready for you. You actually have to choose the memory allocator that you want, and then you can make use of it. Well, that's kind of what we're going to do here with embedded programming in Rust. We're not going to use the default allocator provided by the standard library. We're going to bring in a custom allocator, connect that custom allocator to things like the box, and then we can start making use of box in our code. If you just try to use the regular box in an embedded program, it won't compile because the standard library is not available. But if you take this approach that we're going to look at, you can then make use of box and have some dynamic memory allocation through your own allocator that you've set up. Let's take a look at what that's going to look like here. So, close this, open this file. So what I've done is I brought in a crate here called embedded alloc, and it's going to use a linked list implementation of a heap allocator. I'm not going to get into the details of heap allocators for our session here today, but there are different ways of implementing them. You'll see down here, I'm pulling in this use alloc boxed box. So this used alloc boxed box is actually a lower level library in Rust. You don't typically interact with it because you use the box provided by the standard library, and that standard library box is connected into this. But here, because we're not using the standard library and we're going to provide our own allocator, we're going to access the lower level box, set up our own allocator, and kind of tie it all together. Now, down here, you'll see where I'm going to mark this heap struct. This is my global allocator. This actually has special meaning. This is telling Rust that this will be my global allocator mechanism. So if you use the standard library, Rust would be providing that global allocator mechanism. But in this case, I'm the one providing it because of the embedded programming. So I'm basically telling Rust, use this as the global allocator. So what that means is when I go to create boxes, it's going to be using this mechanism here that we're setting up to do the allocations. Now, if you remember earlier, I mentioned that we would be running unsafe code. And I haven't really talked about this since the first demo, but I'll talk about it now. You'll notice I got rid of the no unsafe macro. And that's because down here, when we go to configure this memory, we're going to have to do something that's unsafe. Essentially, what's happening here with our own allocator is this is a static mutable variable. Static mutable variables violate all the rules of Rust. It's a global variable that can be changed by anybody at any time, which, defeats the whole point of the Rust memory safe programming. But when you're building your own allocator, that's how you have to set it up. See, here's the thing about Rust. Rust, in a sense, does unsafe things under the hood. But Rust exposes to you a safe interface, a safe API that you work through in order to do your programming in a safe way, and you trust Rust to do things properly for the unsafe part. So instead of everybody having to be an expert at unsafe programming, the creators of Rust are the experts at unsafe programming, and then the rest of us just use the functionality they provide. Well, when we're doing this kind of programming, we're having to go much lower level. And so we can't just rely upon the memory safety completely provided by Rust, especially if we want to have our own global allocator. So that's why you see this unsafe code being used, is because we're having to do something at such a low level. Memory safety isn't really a possibility for us. We have to do something that is inherently unsafe. However, you'll notice we're keeping this code limited to this part of the program. Now, down here, guess what I can do? I can allocate my box. Now, my allocator can only handle up to 1K of memory size. So if the things I'm allocating down here exceed that, then we're going to have a problem. But there's only limited memory on the microcontroller as well, right? So, but we can create our box like we normally would. And notice we're just saying box new. This is pulling in the lower level box. And because of this global allocator, this is all tied in together. Now, if you want, you can actually go to the embedded alloc GitHub repo, read through the code on how all of this works. And you can also learn about other heap allocators that it provides to you to work with. So if I go to run this code, there's nothing really super amazing about it. It's just going to run. And when it runs here, it says the meaning of life is 42. That's just printed using the RTT, or the rprint line, I'm sorry. I'm here over RTT, and we're just taking that value and then dropping it here into our rprint line macro. Also, you'll notice I didn't put this in the loop like I did some of the earlier examples. I had this outside the loop. If you're using Clippy to analyze your code, it'll sometimes complain if it sees the empty loop there. So we just put this little thing here. Also, I noticed as we were going through our demonstration here, I didn't have my .vs code folder with all of my configuration for Rust and stuff. I'm going to throw that in following the demonstration, so you get all of the cool linting and stuff. I'm not sure how I missed that, but my VS Code folder there doesn't have that. So I'll add that following today's presentation. And so what would happen is if you didn't have this, Clippy would be complaining inside my VS Code. Okay, let's take a look at the final demonstration here. Now this is the I believe it's the final project from the discovery. It's the snake microbit. And basically it's just a little snake game that you play on the microbit here. So what I'm going to do is I'm going to just stop this real quick, and I'm going to go to that folder. I'm going to say cargo embed. We'll let that flash the microbit. Okay. So I'm going to bring this up so you can actually, let me stop sharing for 1 second. I'm going to bring this up so you can see the colors of the lights. You should be able to see the lights there. Okay. So what I'm going to do is I'm going to play the game here real quick. And the way you play the game is you use the little buttons here to kind of direct the snake. One button will turn it like up and down, and one will turn it left, one will turn it right. That's what it is. And so if I bring this up a little bit, you can see the lights a little better. And if I click this, you'll see now where the lights are moving, and then it eats the food. So the brighter light is the food. The lesser light is the snake. You can see I'm not very good at this game. But anyways, you can play this, and the snake will go around and eat the food. There's another version of the snake program on there too, where the snake actually gets longer. I'm not sure why this snake isn't getting longer. But anyways, you can build little games like this. Now, the cool part isn't really the game. The cool part is coming in and taking a look at all of the code that goes into making the game work. So in the main RS here, it's going to show you how to do things like set the LEDs to different levels of brightness. So like the food is one level of brightness, the snake is a different level of brightness, so on and so forth. It walks you through having basically a little game loop here where you're processing the or where you're updating the display and stuff in response to the game state changing. And then of course we have the interrupts for when you push the button, so on and so forth. If you come into here, the main file here is the actual game file. I'm not going to go through all of this now, but you can go through and read through the code and kind of understand how the game is working. Of interest to me, at least for what we're discussing here, is you'll notice the GPIO. Also, you'll notice the turn number. This is being, or the turn is being also stored as a ref cell mutex. So while the GPIO is an example of something that could be something that is a shared resource, you can also have other data for your application that's also a shared resource. And so you could do that through your own mutex ref cell for those pieces of data. Anyway, it's got a bunch of code here for initializing buttons. You can see examples of that here. Going through and configuring different parts of the application, and another critical section block down there as part of the configuration. And you can just kind of walk through and see how it handles interrupts and things like that. Some of it's similar to the earlier examples that I showed, but you can see how it's interacting with the buttons in this particular case. And then of course over here is the display. And this is where it's going through the process of actually updating the display and how it's handling making some of the LEDs bright, making some of the LEDs less bright. You can take a look at that code over here. Okay, cool. So I think we've reached the end here of our presentation. I appreciate all of you all joining in, and I appreciate your patience with a couple of times there where I shared or didn't share when I wasn't supposed to. I hope this information has been helpful. As you go in and take a look at the content, if you have any questions about anything, put an issue on the repo, send me an email, connect with me on LinkedIn and send me a LinkedIn message, and I'll be more than happy to answer the question or make any fixes to the repo if necessary.